I'm going to talk to you a bit about pond management today. Gathering from the nature of the group and some of the questions people asked during the registration thing, we've got quite a range of people. These folks that are running greenhouses or other horticultural operations and aren't really dealing with ponds per se, but are getting water from a pond or some system to use for irrigation, all the way through homeowners or property owners associations, golf courses, whatever. So there's a pretty big range. What I'm going to cover will address most of these things, and given that people asked some very specific questions in the registration process, I'm covering those at the very end. So we'll move through here. All right, well, pond issues and management, first off, right off the bat, there really isn't a difference between a pond and a lake. Generally, we think of ponds as being smaller and lakes being bigger, but there's no scientific difference between them. I've worked on a local lake here that's 500 and some acres, and it's called Quabog Pond. I've also worked on Mansfield Lake, which is 8 acres. You know, but from the sense of pond as we're using it, we're thinking about a very small body of water, something you could probably skip a stone across, or something you might see in a terrestrial animal swimming across, things of that nature. Processes governing pond condition are pretty much the same as for any water body. It really doesn't matter how big it is. The key factors, though, are the watershed size relative to the pond. You know, how big is the area draining into the pond relative to the size of it? If I have a tiny pond and a really big watershed, it's going to have a lot more water quality problems than a big pond with a small watershed. The soils, the slope, the vegetation, land use, everything that goes on in that watershed affects the water quality, how much algae and plants it will generate. Pond morphometry, fancy word, just means the shape of the pond, the three-dimensional shape and its depth and the depth contours. And then your regional climate. I gather people are mostly from the southeast on this, but they could be from anywhere. I happen to be in Massachusetts. Things are very different here than in Florida in terms of the basic soils, but also in terms of the climate. And that does affect the pond condition. Pond problems, most of the things that you hear about, algae blooms, rooted plant growths, a lot of suspended solids, not necessarily algae, it just could be resuspended bottom sediment, toxic contaminants, and fluctuating water quality, things that go up and down, pH and oxygen being two good examples. Certainly there's other things going on. There's nuisance fauna. There are a variety of things that can affect lakes that will result in problems for people. But for the most part, these are the biggies that you get phone calls about. And those problems are driven by usually elevated inputs of nutrients or sediments, and oftentimes those two go together. Contaminants that come in by runoff or are naturally in the groundwater. There's places with high arsenic in groundwater, and there's places where the runoff from, say, old apple orchards contribute a lot of arsenic. So there's more than one way for almost any contaminant to show up. There's variability that's induced by stormwater runoff. This is certainly a function of climate change. We're getting more intense storms, so we're getting more runoff, which means more variability. And variability is as big a problem in water management and pond management as any change in the average. If somebody says my temperature is going to be a couple degrees warmer, I'm not that worried about it, but I realize that the variability might be that I have spikes of really high temperatures, spikes of really low temperature. That variability can be very tough on the critters living in a pond and on the people trying to use it. Internal processes after inputs occur. That's a sort of an obtuse one, but what I'm talking about there is that once things are put into a pond, they don't just pass through and disappear. A lot of stuff winds up in the sediment, and it can come back to haunt you later. It recycles. This is particularly true for phosphorus, which is a critical nutrient in the aquatic environment. Okay, so why are nutrients a concern? I've mentioned these a bunch of times. I mean, people tend to think, well, nutrients, nutrition, that's a good thing, right? Well, it is to a certain extent, but unfortunately, when we get overloads of nutrients, particularly phosphorus and nitrogen, that's when we get the aquatic problems that really stand out to people, particularly algae blooms. There's a national lake assessment program that goes on every 5 years. They're in their second round of 5 years now. According to them, almost half of our nation's lakes have problems. They're not in good shape. I guess the good news is more than half are in good shape, but still that's not a great average. The nutrients may have a positive connotation in health situations, but that overabundance in a lake basically gives you a fat lake. All right, the impact of phosphorus, two graphs here. One on the top there is simply phosphorus versus chlorophyll. Chlorophyll is the green pigment in algae or any other plant. And you can see this is a lot of data condensed into one little band, but as the phosphorus goes up, the chlorophyll goes up. Pretty straightforward relationship. Somewhere around that 200 microgram per liter, which is the far right of the graph, it does sort of level off. You don't get infinitely more chlorophyll with infinitely more phosphorus. But this is where the root of most aquatic problems comes from. Too much phosphorus gives you too much plant productivity. The bottom graph is just showing what happens to the clarity of the water. Interestingly, it's not a line, it's not a linear relationship like the top. The initial loss of clarity as phosphorus goes up is pretty steep, and then it kind of levels off over time. It's a function of the particle distributions and sizes and a lot of other complicated stuff, but the bottom line is a really clear lake can't have much phosphorus. A very turbid lake probably does have a lot of phosphorus, but the relationship over the space going from no phosphorus to a lot of phosphorus isn't necessarily linear when it comes to the clarity. This graph is, it's not the prettiest one I've ever seen, but it sure is one of the most useful. All this is really saying is that as the phosphorus goes up, the percentage of the algae, the phytoplankton, in cyanobacteria, or blue-green algae, also goes up. In other words, everything else either declines or is sort of stable, and this may not hold in every single lake, but from literally thousands and thousands of lakes that they put into this process, as you go from very low phosphorus down around 10 micrograms per liter up to very high phosphorus up around 100 micrograms per liter, you go from blue-green algae or cyanobacteria representing less than 20% of the algae to representing literally 100% or more. Well, it can't be more than 100%, but getting a lot of the algae as cyanobacteria. Cyanobacteria, although there are ones that grow in clean lakes, there are some that are very useful in many ways. For the most part, cyanobacteria are the bad actors in the aquatic environment. They create taste and odor. They create toxicity, they clog systems, they form surface scums, they cause wild fluctuations in pH and oxygen. They're really not something you want in your lake in any great quantity. And of course, as the phosphorus goes up, the chlorophyll and the algae go up, and as the phosphorus goes up, more of that algae is cyanobacteria. So that's a real issue. Okay, I don't want to ignore nitrogen. It's generally true that phosphorus controls the quantity of algae. Nitrogen controls what types of algae will be present. When the nitrogen-phosphorus ratio is low, and low is something like 7 or 10 to 1, so it's still more nitrogen than phosphorus, but when it's relatively low, that favors cyanobacteria. Most situations where people are letting sewage or fertilizer or things with very high levels of nutrients get into the water, it's usually a low NP ratio. If you think in terms of the typical numbers you see on a bag of fertilizer, the ratio between the nitrogen and the phosphorus, the first two in that usually, tends to be fairly low. We tend to add a lot more phosphorus relative to nitrogen in fertilizers. That isn't always true, and there's even phosphorus-free fertilizer. But generally speaking, that's what happens. That low NP ratio with lots of phosphorus to begin with leads you to blue-green algae blooms. Okay, cyanotoxins, I don't want to belabor this too much. I'm not into scare tactics, but there are toxins that are produced by many types of blue-green algae. Some of the ones pictured here, Microcystis, Aphanizomenon, and Anabaena are three of the most common blue-green algae. They're also ones that produce some pretty potentially high toxin distributions. This is widely distributed in the aquatic environment. It's not harmful to plants, so if you're running a horticulture operation, it's not a threat, but it is to animals and people. They can be liver, nerve, or skin toxins. If you have to make a choice, go for the skin toxins. But liver and nerve is not good. They're selectively produced, and they're not always produced by the same strain in each case. So it's kind of confusing. Nobody thoroughly understands this yet. They're out in the environment, widely distributed, but it's pretty rare for them to be at acutely toxic levels. So you do not need to live in fear of this, but you should be aware of it. Some other algae also produce toxins. One called golden blossom, which is pretty abundant in Texas and some of the other southern areas, not Florida so much, will kill fish. There's marine dinoflagellates, they call red tides, black tides, brown tides, things of that nature that have been toxic as well, although those don't exist in a toxic form in freshwater. So cyanobacteria are really the primary toxin threat to people in freshwater. There's been pretty good research. I happen to be the editor of a journal called Lake and Reservoir Management. There were 3 papers that got published in September 2009 altogether, one looking at the distribution of toxins in Minnesota, one in Missouri, and one in Florida. And it was pretty much the same story everywhere. Widespread occurrence, variable concentrations, but generally not found at high or really, scary levels. That's a rare occurrence. Water treatment in most facilities does an excellent job removing those toxins. So when you're drinking publicly treated water, you're at minimal risk. The real risk comes from either substandard treatment or direct recreational contact. People swimming in this stuff is the biggest threat. Okay, so the sources of nutrients. Where do these nutrients come from that fuel these problems? Certainly there's natural background. For those of you in Florida, you have a lot of naturally fertile lakes. Phosphorus is very high in the sediments there. Up in my neck of the woods and even further north, not so much. Lakes tend to be very clear because there isn't very much phosphorus. Fecal material of any kind will add a lot of nutrients, phosphorus, nitrogen, and other things. That could be human waste. It could be domestic or farm animal waste. Fertilizers, real good source of nutrients. That's their intent, but not when you get in the aquatic environment. Stormwater runoff isn't really a source itself, but it's a conveyance that brings contaminants, including nutrients, across impervious surfaces like roadways or even well-packed lawns and gets them into the aquatic environment. Internal recycling, I mentioned before, that's the ghost of loadings past. Nutrients can come back out of the sediments by a variety of mechanisms and be available for algal production or rooted plants again. In the background picture in this, you're looking at a bunch of pond muck that was scooped up and put in the pan. Just a close-up shot. Looks like chocolate pudding, but not nearly as delicious. All right, magnitude of nutrient loads. So what's a high number, what's a low number? Well, if you can get below 10 micrograms per liter for phosphorus, you're doing great. You're not likely to have any problems. Poor is anything over 100. And I can tell you that naturally 100 occurs in many Florida lakes. I've seen 200 and 300 even. Background concentrations in natural lakes, typically 5 to 50. So the low end of the range, but they can be moderate at least. When you throw in urban runoff, now you're talking much wider ranges with an average or median somewhere between 370 and 470 micrograms per liter. That's from a very, very large study done over the space of about 20 years. So it's pretty good data. The point is those are big numbers. If you have urban runoff, you have very fertile water. Agricultural runoff, same deal, similarly wide range. In the case of feedlots, outrageous numbers. I mean, really, really high. So urban runoff and agricultural runoff can be huge problems for the aquatic environment in terms of nutrient loading. Sediment issues, they tend to go hand in hand with the nutrient issues, although not always. The picture in the sort of, well, the lower half, but the upper right of that is a clay liner. You can actually see the gray clay to the right-hand side, and then all the black muck that's accumulated since that clay liner was put down. In this case, it was about 200 years ago. So it's not a huge sediment accumulation, but all that black muck is a real problem in terms of the internal recycling. And of course, it makes a very fertile substrate for plants to grow. Right below it, you're seeing a drawn down lake, and you're seeing the huge sand delta that came out of one storm drain. On the left side, one of my favorites, that's the Grand Canyon of Chicopee, a place nearby here. All that was a little 6-inch drainage pipe off a parking lot at the top of a very sandy slope. And you can see the chasm that it created as a result. That is a full-size tree down in the bottom there that fell in from the top. Sedimentation and movement of sediment with water is a fact of life, and you can fill in a lake or pond pretty darn quick if they don't keep it under control. Okay, issues with toxic substances. I don't want to belabor the points, but just so you're aware, again, we have cyanotoxins, which we've already addressed. Pesticides and metals. So those of you working in horticulture, the metals probably aren't an issue, but the pesticides are. Most toxic compounds get delivered in runoff or some sort of direct discharge. They can accumulate in the sediment and make later remediation difficult. If you have a sediment loaded with this sort of stuff, there's almost nowhere you can take it if you want to dredge it out. So that becomes a real problem for rehabilitation of lakes. And of course, pesticides don't do much good when they're allowed to leave the target area, so people don't want to put them in the aquatic environment. You want them on the crop or the flower or wherever else to protect it, but unfortunately, wind, water, and so on have a tendency to move these things downstream. Climate change issue, again, warmer temperatures favor cyanobacteria and rooted plant growths. Variability favors adaptable organisms. Unfortunately, the blue-greens and many of the invasive plants are very adaptable. The picture in the middle, slid up slightly up from the others, is hydrilla, extremely common in the southern United States and has really taken over a lot of lakes. We are now finding it in the northern states as well, and it really takes over. Okay, just a couple notes on invasive species. This is mostly about nutrients and water quality, but since at least a good portion of you are in the horticulture industry, there's very, very extensive documentation that a lot of our invasive species came in the ornamental horticulture trade, including the aquarium trade. Please be very, very careful with what's coming in and what's going out. Once an invasive species gets into a pond, it's extremely difficult to eliminate. They can gradually spread to other systems. In fact, it's almost inevitable. And the cost of prevention is far lower than the cost of remediation or the lost opportunity and utility. So it's really important. That picture on the lower left happens to actually be a nursery in Vermont, and they were selling water hyacinth, which is a real scourge plant if it gets out into lakes. Fortunately, it doesn't tend to overwinter up here, but they were just selling it to be ornamental stuff in a pond. The one on the right is actually parrot feather, also sold ornamentally. It can be very pretty in a little patch, but boy, it can take over a pond. So these are things that oftentimes folks in the industry don't understand the potentially negative consequences of what otherwise looks like something pretty.